Welcome. So we're going to finish off a little bit from last time. So we talked about capacitance last time, and we talked about the basic definition of capacitance is the measure of the charge you can store in a capacitor divided by the potential difference that is placed across the capacitor. And we did some various skills, and then we talked about a parallel plate capacitor, and we developed, and this, I'm sorry, this has a bit missing, it's epsilon naught of a permittivity of free space times the area of the plate, of the gap basically between the plates, and then over the separation of the plates. And then if we put a material, an insulator in between, we call it a dielectric constant. And that's a multiplication factor. That actually just increases the amount of charge we can store on the capacitor, as we talked about last time. There's a fair amount of technology involved in trying to develop better and better dielectrics. And then we did a couple of problems, and I think we ended up here where we ended talking about series and parallel capacitors. And we mentioned that basically a parallel series, we call this a network, a parallel network of capacitors effectively increases the area without changing the gap. So if we work on the principle that capacitance equals epsilon naught area over the gap, so with a K in front of it, then if I increase the area, I increase my capacitance. So you can imagine just like pushing these guys together so it's a solid connection. It's just, you just made a bigger area capacitor, and so it has a bigger capacitance. So it's no surprise that when you connect capacitors in parallel, then you connect C1 to C2 to C3. Question or comment?
Question. Is it K epsilon A, or is the formula supposed to be Ka epsilon?
Does it matter? I mean, if you think about it, you're just multiplying the things together. So I write it down different ways at different times. So don't worry about that. And then over here, what we're doing is, now here's another thing that it's a bit subtle, but there's no electric field or a steady state. At steady state, when everything's charged up, there's no electric field in these wires. So basically, you can imagine shrinking them. So basically, that top plate goes down to there, and the bottom plate, the red plate, comes here, and then we have the. So then that goes there, and 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 that goes there, because these guys just can be shrunk to nothing. And then imagine just pulling these two plates out, so we end up with that. So we end up with a capacitor which has the same area, but just a bigger gap. Just take all the gaps and add them together. So I can use that to justify the idea that 1 over the capacitors, the series combination of a capacitor, is equal to 1 over C1 plus 1 over C2 plus 1 over C3. It's worthwhile learning those. Frankly, when we get to resistances, we're going to find the rules switch. So if I just R series equals R1 plus R2 plus R3, and 1 over R parallel equals 1 over R1 plus 1 over R2 plus 1 over R3. And my advice is you learn them one way and you recognize that the other thing is the opposite. If you try to learn them both, sometimes you can get mixed up. So I learned it for resistors, and I know the capacitors behave the opposite way. I have a good feel for why as well. But most common mistake on these is people just get the wrong equations, or they don't complete the equation. Did we do these? Yes, we did, didn't we? And we even did this one. And the trick with these is it's like eating spaghetti. It's like, where do you begin? And you begin with the parallel because it's the combination that's unambiguous. And you bring it down to a single capacitor in series with 2 other capacitors, then you solve the series combination. And if I just play around with this a bit, another good example is I do that. Let's actually play with this a little bit. So how would you solve this one? Let's say this is C1, C2, C3, C4. I'm not worried about the values, but where would you begin? What would you... You'd add C3 and C4 together because they're unambiguously in series with each other, so that would take you down to this. Now what would you do? C2 and the combination C3, 4. You do that bit next. And then that would take you down to that, and you'd combine those. Yeah. So it's really useful to pick away at these things because they're relatively simple circuits, but they're not. And the rules you're going to use are relatively simple. They're just people when they first see them are just a bit overwhelmed. The other thing that is also to be borne in mind is that I can make the circuit look very different. So I can have that. Whoa. Well, actually, I don't like that. Let's do that. So what's going on here? And the trick is, well, you straighten that bit out to begin with. So let's call it C1. C1 goes on top. Then you come down, and then you have a junction, a junction, a junction. So I have 3. Let's give those names. C1, C2, C3, C4. C2, C3, C4. I come out of these two, and that's C5. But this guy, C4, goes down here. So these two are in parallel. So how would I attack this? I'd do that first, leaving that one out. I'd do that combination second. I'd do that third. I'd do that fourth. Yeah. So it's worthwhile playing around with different layouts. Now, I tend not to give you a whole huge variety of layouts because I think it comes a bit fast, but, you know, and there are kind of like, when you look at circuit diagrams, after a while, you will get comfortable with them. But at the beginning, it's quite disconcerting. So it's worthwhile, although I'll tend to use circuits that look like this, I'm showing you the principle of it, not practicing you in the more detailed parts of it. So get yourself more practiced. Can I ask you a question? Just show of hands. How many people here so let's actually use this thing. I want you to vote. Okay? If you have ever built an electric circuit, press A. If you've never built an electric circuit, press B. If you've ever, constructed an electric circuit, press A. If you've never done it, press B. I'm just curious. I don't know the answer to this. So we got about 4. This is about right, okay? Let's stop it and have a look. So most people have built a circuit, but it's about 2/3, 1/3. Okay. Let me ask you another question. If you own a soldering iron, press A. If you don't own a soldering iron, press B. Stop that. So again, it's about basically 2/3, 1/3, but going the other way now. If you know what a breadboard is, press A. If you don't know what a breadboard is, press B. A breadboard? Breadboard. about a third. So let me ask you a final question. If you're going to be a EE person, press A. If you're not, press B. One more person. Oh, okay. Well, as long as the people who are doing it are going to be EEs and not vice versa, it's not so bad then. One final question. A hobbyist is somebody who plays with stuff. Hobbyist might be somebody who makes stuff with woodworking. Hobbyist might be somebody who builds rockets. A hobbyist might be somebody who is an amateur radio person. A hobbyist is somebody who constructs things somehow. In any area. Hobbyist could be a programmer. Hobbyist could be somebody who builds their own computers. Are you a hobbyist? If you are, press A. If you're not a hobby, if you don't consider yourself a hobbyist, press B. Press B. So about, again, 2/3, 1/3. Okay. You know, I would commend you to be a hobbyist. I know that you got a lot to do, and it's not that I'm, you know, trivializing the fact you're probably working and you're probably doing full-time school. But if you can get some time together to kind of play with this stuff, every teacher complains about the fact we just don't have enough hours in the day to kind of get your skills to where we'd like them to be. And what we do is we give you the big picture, and what you miss out on is some of the detail. There's some of the stuff you can only get by just messing with stuff. So if you're going to go anywhere near electrical engineering, or I would say computer engineering, I would, you know, go along to something like Radio Shack or something and get yourself a soldering iron, some solders, and a little book on doing circuits, and just play. Just make some silly projects. You know, if you're going to be around machinery, join a club like there's the Hackers Shed or whatever it's called, or Hackers Place. Get some experience. Try and get yourself to the stage where you're more than book smart, because you're going to eventually need it. And also, you're here for a reason. Presumably, you like this kind of stuff. So you might find that when the going gets tough, and the going will get tough, it will get boring and it will get tedious sometimes. It's maybe that kind of thing that will carry you through, where you go, I know why I'm doing this, because I kind of like this kind of thing. So anyway, there's my words of wisdom. Last little bits on this. We spoke about the fact that capacitors can be used to store, well, they store charge, but the reason why we might want to store charge is as an energy storage device. It's not a particularly good one compared with a chemical cell, for example, but it's very clean in a way. You can put it in a very hostile environment and it will do the job. So here I'm imagining two parallel plates. I've got a D separation, got an area A, got minus Q on one plate, plus Q on the other. We say consider charging up a capacitor. As the charge increases, the potential difference between the plates increases. So that's a little bit, hold on. I have a voltage. What kind of voltage is that? That's an EMF. And I have parallel plate capacitor. This is 6 volts. When I first begin, there's 0 volts potential difference across that. Well, no. Okay, I got a shame on me. I'm doing an unrealistic circuit, so let me sort that out. This is more realistic. You can't build a circuit that doesn't have resistance, so I have a resistor there and a capacitor there. I have 6 volts EMF. That's what my battery's putting out. There's no law says that the 6 volts has to be all across the capacitor. In fact, it doesn't. So what happens initially is that you have basically no charge on the capacitor, so no potential difference across it. No charge on the capacitor, so no potential difference across it. So the 6 volts is all across the resistor. Big current flows. That's like cars arriving at a parking lot. As time passes, I get more and more charge on here, so I get more and more potential difference across here. If I've got more potential difference across the capacitor, I've got less potential difference across the resistor, because it's got to add up to 6. So less current flows. That's because cars are finding it harder to find a parking space. Finally, I've got maxed out charge on my capacitor. I've got all the potential difference across the capacitor. It's 6 volts. I've got no potential difference across my resistor. There's no current flow. I'm fully charged. So it's useful to talk about the voltage of a voltage source as an EMF and the effect of that voltage on a component as the potential difference. They're both measured in volts. I think of it kind of like the difference between salary and rent and you know, spending money. I use my salary for rent and spending money, sometimes more, sometimes less. What I spend adds up to what I earn, unfortunately. You know, so it's kind of like it balances. Same kind of thing for this. So here we say the potential difference between the plates increases. So what happens is initially there's no potential difference across the plates because there's no charge. But as I put more and more charge on, I get more and more potential difference. Consider an instant when the charge on the capacitor is plus Q. The associated potential difference is delta V equals, well, delta V equals Q over C. The work required to transfer a little bit of charge across the capacitor is the little bit of work is equal to Q over C, the potential difference, times Q. Remember, delta U is equal to Q delta V. We did that before. So delta W equals delta U. That's from the work energy theorem, yeah? The amount of work is equal to the amount of energy. So delta W is equal to delta U, which equals Q delta V. So delta W, or dW, is equal to delta V times dQ. And delta V, we said, was Q over C, so we have Q over C dQ. Okay. The total work required to charge up the capacitor from 0 to big Q is it's the integral from 0 to big Q of Q over C dQ, and I can do that. That's just going to be increase the power by 1 and put it in the denominator, so 1/2 Q squared over C. That comes from the calculus bit. Let's do it a bit more visually. Here's my voltage, here's my potential difference, if you like. Here is my charge. I start off with no potential difference. I end up with a ton of potential difference as I go from no charge to a lot of charge. Let's draw it out. Oh, look. If my potential difference is in joules per coulomb and my charge is in coulombs, what's the area under the curve going to be? Joules per coulomb multiplied by coulombs gives me coulombs, joules. Joules is energy or work. So I can get from my simple graph, the area under the graph is going to equal to the energy stored, the work done on, which equals the energy stored. So I didn't need that calculus. I could have just got it from, it's a triangle, so it's a half the base. It's going to be 1/2 the base. The base is Q times the height, which is delta V, which equals R. So now I got two slightly different forms to it, but we can figure it out. I just did that one from the graph. I did that one from calculus, and they're the same thing. We can rearrange, so a half of Q times delta V, and remember that Q equals delta VC. So what you can say is, let's substitute in for Q. So this equals 1/2 of delta V times C times delta V, which equals 1/2 C delta V squared. Okay, let's substitute in for delta V. 1/2 times, rather than delta V, I'm going to put Q over C times Q, which equals 1/2 Q squared over C. So these three equations are all saying the same thing. The difference is you're just substituting in for that base equation. So I don't bother learning three of them. I know one of them, the one that I'm most familiar with is that guy, because it comes from the diagram, and I can figure out the other two. When I'm doing a lot of homework in this, I can just write them all three of them down. But, you know, in my long-term memory, I have the middle one pretty well to write. How much energy is stored in a 6 farad capacitor that holds 5 coulombs of charge? So I've got my delta U is equal to 1/2 Q delta V. And what do I know? I know C is equal to 6 farads, and I know Q is equal to 5 coulombs. So I've got to do a bit of rearranging here. So I'm going to remind myself of Q is equal to C delta V. That's my other recollection. So then I want to, I don't want to talk in terms of delta V. I want it in terms of C and Q. So let's get rid of the delta V. Oh yeah, 1/2 Q. Let's get rid of the delta V. Q over C, which equals 1/2 Q squared over C. Put some numbers in. 1/2 Q is 5 over C is 6. So this is equal to, it's going to be 25 over 12, which equals what that's going to be, 2.1, and it's going to be joules. Cool, did I do that right? I've not got any answers down here, so let me just double check briefly. Q is 5, so that's going to be 25, and B is, yeah, 25 over 12. Cool. How much energy is stored in a 9 farad capacitor is fully charged by a 9-volt battery? Ah, okay, so now we're just making it a bit more interesting. You shouldn't really put it down without a resistor in it, but you know, the resistor, when it's fully charged, is no longer doing anything in the circuit, so we can cheat a little bit. 9 farads. I'm going to say delta U is equal to 1/2 Q delta V. And what do I know? I know my delta V equals 9 volts, and I know my C is equal to 9 farads. C and delta V, I got to rearrange something, so charge equals, is that right? Charge equals, yep, that's right. So then I can rearrange. What do I want to get rid of? I want to get rid of the Q because I want it in terms of the other two things. So 1/2 C delta V times delta V, which equals 1/2 9 times 9 times 9. Oh, wonderful. 9 9s are 81. 9 81s. 4 1/2 81s is going to be about 300 and something. Let's just use our calculator. So it's going to be 9 caret 3 divided by 2 equals 364.5. Am I right? It's going to be joules. So not bad. And that is at the end. No, a bit more. How much energy is stored in the capacitor? Okay. So we say that, all right, there's energy, so how is it stored? It's stored in terms of the electric field. That's what you're creating. So we say energy that is stored in the capacitor is stored in the electric field between the plates. Delta V equals minus ED. We did that last time. That's potential. And C equals epsilon naught A over D. I could have put the K in. It's just, let's keep life simple. So energy is equal to 1/2 C delta V squared. That's one of my 3 equations, which was 1/2 epsilon naught A over D. That's my C times minus ED. That's going to be squared because it's V squared. Turn the handle 1/2 epsilon naught A D E squared. Where's my D gone? That D's gone with that D squared there. So U is equal to 1/2 epsilon naught A D times E squared. Does it make sense? It's a constant times a constant times the area. If I have more area, I expect to be able to store more charge. That makes sense. That's interesting. Times the separation. That there is a volume. That's the volume inside the capacitor. That's interesting. The more volume for a given situation, the more electric field, you could argue. And then multiply by E squared. Why is it E squared rather than E? It comes out of the math. I don't have a quick justification for you of why it should be E squared, but it is. So you can think about that. Remember, I would not expect you to recall this equation. You could derive it, but I don't mind giving it to you and asking you to use it, so make sure you know what all the letters stand for. Okay. The other thing is energy per unit volume. So just take your energy and divide it by the volume. Well, the volume is there, so it's just going to be 1/2 epsilon naught times E squared. That's very clean, isn't it? The energy per unit volume is just a constant times the electric field squared. If I doubled my electric field, I quadruple my energy per unit volume stored. Why does this matter? It matters because when you look at a capacitor, how much energy can you store in it? Do I need a capacitor the size of this room, or do I need a capacitor the size of a deck of playing cards? That's the kind of things that it's useful to be able to figure out. This expression is valid for many different capacitor configurations. We tend to think about parallel plate capacitors, but there are other configurations. The energy density of an electric field is proportional to the square of the magnitude electric field at a given point. So, energy density of any electric field. Oh, okay, cool. I think that's it. Yes. So let's pause there, and we'll take a bit of a break while I just put this into